We are examining a system engineered for maximum velocity. The blueprint for this architecture is the Solana white paper, authored by Anatoly Yakovenko. The structural question is whether the world's fastest blockchain relies on a mastery of applied cryptography, or if it hits that speed by operating as a heavily optimized centralized database. The document outlines a network theoretically capable of processing 710,000 transactions per second on a standard gigabit connection. To understand how it reaches that number, we must isolate the primary bottleneck in distributed systems. That bottleneck is the absence of a trusted global clock. Determining whether Solana solves this timing problem with decentralized cryptography or sheer physical engineering will define the true nature of the network. Historically, Byzantine fault-tolerant state machines reject timestamps entirely. A decentralized network cannot trust a time recorded by an individual node, because any individual node can lie. Instead, traditional blockchains require thousands of independent nodes to constantly pass messages back and forth across the globe. They must continuously negotiate and vote to agree on the exact order in which events occurred. This exhaustive negotiation process is defined as communication overhead. Because every new node adds another layer of required verification, the network's throughput inevitably drops as the number of independent participants increases. Achieving network agreement on time is the mathematical ceiling for traditional decentralized systems. Bypassing that ceiling requires a complete architectural rebuild. Solana bypasses this limitation with proof of history. It is a specific cryptographic solution designed to eliminate network communication overhead. The clock runs a continuous SHA-256 hash function. The first equation's output loops directly into the second. Because it's collision-resistant, calculation cannot be predicted. #200 strictly requires #199's completed output. The sequence must be fully executed. To timestamp a transaction, the leader appends arbitrary user data into the active hash loop. This permanent injection alters every subsequent hash, definitively proving the transaction occurred before following hashes were calculated. This creates a crucial distinction. Proof of history is strictly a cryptographic clock. It is not a consensus mechanism at all. By replacing network voting with mathematically verifiable physical computation, the network solves the problem of decentralized time without requiring trust. Generating this timeline demands a CPU core running sequentially at maximum capacity, making creation intentionally slow. But when the leader broadcasts the completed sequence, the verifier nodes can shatter the completed timeline into thousands of independent slices. A modern GPU can check every single slice simultaneously, auditing the entire timeline in a fraction of a millisecond. To generate that timeline, Solana designates a single machine in the network topology as the leader. Every incoming user transaction bypasses the broader network grid, funneling directly into this central leader node. The leader orders the messages locally, arranging them to maximize throughput before passing the pre-packaged state downstream to the verifiers. Funneling all traffic through a single computational choke point is the absolute structural trade-off required to eliminate timeline arguments and achieve velocity. Once perfectly ordered, the transactions must be executed. Traditional architectures process smart contracts sequentially, making one update to the global state at a time. Instead, Solana processes all of them in parallel. The software layer handling this routing is an execution environment built on Extended Berkeley Packet Filter Bytecode, or eBPF. The eBPF environment isolates independent programs that are not interacting with the same data states. It intentionally suspends local operations and calls upon the hardware layer, specific hardware-level functions known as GPU intrinsics. The massive GPU executes these batch tasks, processing thousands of cryptographic verifications simultaneously before returning the final result. Utilizing specialized hardware in this manner converts the blockchain into a parallel data center processor, separating it from consumer-grade network architecture. This continuous demand for parallel processing and sequential hashing dictates the physical reality of the network. Operating a verifier node requires a gigabit connection and extreme memory throughput to maintain a state table of 10 billion accounts. While a 4,000-core GPU is often cited for the task, it was established in the white paper as a baseline testing benchmark to calculate theoretical hardware limits. This chart details the steady-state memory access limits from the original white paper tests. The 710,000 transactions per second peak was not achieved on a global decentralized network. It was calculated directly on an Amazon Web Services data center instance. Sustaining that speed creates an immediate problem. To manage the massive volume of historical data generated, the white paper relied on streaming proof of replication, where secondary archiver nodes would continuously encrypt and store the data. In practice, the physical burden of encrypting compounding terabytes of data forced the archiver nodes to be phased out entirely. The white paper's data management model proved mathematically unsustainable for decentralized participants. Proof of history provides a mathematical resolution to the problem of distributed time. The cryptographic clock operates exactly as designed, structurally distinct from Byzantine fault tolerance, which the protocol handles externally. But the theoretical benchmark of 710 transactions per second lived exclusively inside an isolated Amazon data center. The theoretical storage plan failed to translate to a live protocol, resulting in the death of the archiver node design. These failures define the chasm between a theoretical architectural document and the physical limits of a live distributed network. The continuous SHA-256 sequence provides a verifiable chronological record, but that velocity is not a product of decentralization. Solana achieves its extreme speed through structural centralization, specifically by utilizing a single leader node choke point and demanding enterprise-grade hardware. To strictly evaluate the network's economics, run your own numbers. Check the data on fees, profits, and hardware costs at calccrypto.com. It is the mandatory next step for serious protocol analysis.